Lesson 3.9, Day 2. Pause the video, read the question, and then start it back up. One of the things that you'll be given is volume in a cone, which is 1/3 pi r squared h. For this particular problem, as we practice reading and pulling out the information, you can see some of the numbers are already marked in the photo. What's not marked is we have the liquid that's leaking out. If it's talking about liquid and leaking out, then that to me is referencing volume. To solidify that, we keep reading. It says rate is derivative, and then notice the label. It's cubic centimeters. So what do I know? dV dt is equal to -12 cubic centimeters per second. The height and base are marked in the diagram. Those are for the cone itself. Then you notice there's another marking here because the liquid level is changing. Its radius and height will also be changing. It talks at a moment, it will be 10. So x equals 10 centimeters at a moment in time. You're trying to find how fast is the fluid level dropping. So the fluid level is this marking here of the x, which in our case is the height. So dH dt is the unknown in our particular situation because x is referencing the height, h. Looking at everything I have, there's no mention of the rate at which the radius is changing. And because in this problem there's a geometric connection, we are going to substitute in for r in terms of h. Only because, if I go back to geometry, the 20 here and the 60 here, this would be at a right angle. That triangle is similar to the triangle that makes up the water level, which is right here. So the 20 is to 60 as r is to h. So basically 1/3, move this over here, h is equal to r. That's a direct connection between the two variables. I can go back up to my volume formula now and say 1/3 pi times 1/3 h being squared times h. Remember, in general, simplify before you take derivatives. If I simplify, I'm avoiding product with chain rule. So volume is equal to 1/27 pi h cubed. Much easier approach to deriving. dV dt is equal to, you have your constant multiplier in front, times the derivative of 3h squared because h is changing, dH dt. If you wanted to, you could go directly to this next line. You don't have to do this line here. dV dt is, think of it as the 3 coming down in front. It's multiplying. We get 1/9. Keep the pi constant, h squared, dH dt. Whatever works best for you. The dV dt we know is -12. Plug that in. We have 1/9 pi. And then h, the height at the moment we care about, is 10. So plugging this all in, that's my new equation connecting the change in height. Doing some multiplication here, I get -108 divided by this quantity, which is 100 pi. That is my units here for the, or that's my label for the change in height. The units I need are centimeters per second because this is a linear dimension. In answering the question, you can do it either exactly or 3-place decimal accuracy, and you could say the fluid level drops at, and then you could either say 0.344 centimeters per second, or you could say the 108 over 100 pi centimeters per second. Do not say fluid level drops and then include a negative. That would be double negative, which would go positive. Take a moment, pause the video to read the next problem, and then join back. you have this length here, which is the plank. A plank is a fixed length. So I'm going to mark it 10 feet because it is a fixed length. It's being pushed up, which means this length down here, they're talking about pushing it towards the wall. So we have a changing length here along with the changing angle, because it's asking how fast is the acute angle increasing. So that means we have a change in theta with respect to time that is unknown. We also have, at a moment in time, the plank is 2 feet from the wall. So x equals 2 feet at one particular moment. Because it's being pushed towards the wall, that means this is a changing length, and dx dt is equal to 6 inches per second. Being pushed is decreasing the distance, so I'm going to say negative. You want to be on the lookout for units. These are in feet, this is in inches. Quick conversion, we have a negative half of a foot per second. Then I have all the information out, I know what I'm looking for. I go back and say, what's the connection between the angle with the adjacent side and the hypotenuse? Hopefully everybody's thinking cosine of theta is equal to x over 10. Then derivative, negative sine theta d theta dt is equal to 1/10 dx dt, because x over 10 is like 1/10 times x. Then my sine of theta, well, I go back to the picture and I don't have the opposite, but I could easily find that opposite length by saying 2 squared plus, we'll say b squared is equal to 100. So I get the value of the square root of 96 for the length of the opposite side. So negative square root 96 over 10, opposite over hypotenuse, looking for d theta dt, is equal to 1/10 times our given negative 1/2. Some quick algebraic manipulation, the 10s are gone, so then the d theta dt is equal to 1 over 2 square roots of 96. The measurement for angles is radians per second. Reading the next one before we actually do it together. A lot of information in this problem, but we want to cross-check what's marked with what we have. The 3 feet long is marked here, 2 feet across up here, 4 feet deep right here. Water flows in at a rate of 2 cubic feet per minute. The water, that's the volume, feet cubed is volume, so that means dV dt is equal to 2 cubic feet per minute. How fast is the surface rising? Well, the surface is right here. The amount that it's rising would be the change in the height. So dH dt is what we don't know. Alright, it's at the moment when the h is equal to 1 foot. Well, to figure out what volume formula I'm going to use, I'm going to look at this facing me, because these triangles are the parallel bases. So that means to find the volume, I take the area of the base times its given height, if you think back to geometry. So volume equals 1/2, because I'm working with the area of the base. Now the base of this triangle, we reference the length is changing here, and this piece is called x, but it's only halfway across the whole base, so I'm going to change it to a 2x. The height of the triangle is this one right here, which is h, and then how far back it goes, or how far up, if you pictured it tilted on its side, would be 3. The simplified volume equation is 3xh. As before, I have a variable that's unaccounted for. I'm going to look for a connection. The connection in this one is that we have a triangle here, with the liquid, and then we also have the original triangle to go with the trough right here. So the marking that I have is x is to h here for the water level is to, and then up here I got to make it match. Since it only did halfway, I'm doing half of 2, which means this length is 1. 1 is to 4. So x is to h as 1 is to 4, or x is equal to 1/4 of h. My volume formula is 3 times 1/4 h times h. Again, totally simplify before you derive. dv dt is equal to 3/2 h dh dt. What do we know? We know 2 for the dv dt. 3/2 times the height at our given moment is 1, and then we have dh dt. Solving for the change in the height, we're going to get 4/3. The label for a changing height, it's linear, so it's feet per minute. Take a moment, pause the video, read the next problem. I'm going to do mine from a perspective of I'm up above in the air and I'm looking down, and what I see is this scenario. Here's the shoreline. There's a beacon out here that's on a ship. And what happens is the beacon is going to come and the beam of light will hit the land at different points, at many points. What we care about is that it's directly across and makes a perpendicular, and then at a moment it's going to go over here and connect with the shoreline to make a 45-degree angle. But this is only at a brief moment in time, so it's a changing length. So we say theta equals 45. You're fixed on the ship away from the shoreline at 4 kilometers. So that's a fixed length. What are we looking for? How fast is the beam moving along the shoreline? Well, the beam, depending on the rotation, either this way or this way, but this is the distance along the shoreline here, x. I'm looking for how fast it changes. That's going to be dx dt. Then I look at the other information that was given. It makes 1 revolution every 10 seconds. Well, the revolution is movement in a circle, which is impacting theta, because when this is 45, this is 45. So that means the change in the angle with respect to time, since it goes all the way around, a complete rotation is 2 pi, it does that in 10 seconds. So pi over 5 radians per second is the rate at which the angle is changing. I have to connect 4x and theta. Tangent of theta is equal to 4 over x. Deriving, I get secant squared theta d theta dt is equal to, think of this as 4x to the negative 1. Its derivative is negative 4 over x squared times dx dt. The secant is what I'm finding first. Well, I'm in a 45, 45, 90 triangle. So in any 45, 45, 90 triangle, what's your connection? 1, 1, root 2. Secant is the flip of cosine, so I need my hypotenuse over the adjacent. I'm going to take a root 2, square it. The d theta dt we said was pi over 5. Negative 4 over, I need the x at this moment. Well, because it's 45, 45, 90, that's got to be a 4. And then I'm solving for dx dt. Left side becomes 2 pi over 5, equaling negative 1/4 dx dt. Solving for dx dt, I am getting negative 8 pi over 5. It's talking about a length along the shoreline, so I'm going to say it is kilometers per second, referring to the fact that we're using kilometers here. And then depending on the orientation, we don't know if the beam is going this way or this way. So I would personally say the beam is moving at 8 pi over 5 kilometers per second.